simultaneous and serial monitoring system. My name is Dongmei Dong. I'm from Florida International University. It has been reported there are more than 1,800 types of volatile organic compounds found in different biofluidics. Breath and skin potential sources of volatile organic compounds account for about 54% of total amount. These sources are visible for either invasive or non-invasive detection of VOC for diagnosis of disease. There are different types of sensors for VOC detection. One type is an electrochemical fuel cell sensor. Firstly, we need to talk about what is fuel cell. Fuel cell is a device that converts chemical energy into electrical energy and heat through the electrochemical reactions. The fuel cell components are anode, cathode, membrane, catalyst, bipolar plates. The mechanism is redox reactions. At the anode is a oxidation reaction, and the cathode is a reduction reaction. Fuel cell has a high energy conversion efficiency without the loss in thermal or mechanical energy. This is a diagram of the fuel cell setup and pictures at our lab. We use a mass flow controller to control the flow ratio. It's connected to the visualized mechanical flow meter. This is a fuel cell stack. This is a combustion gas detector. To humidify the gas, we include the bubblers here in our setup. This is an interior photo of the fuel cell stack. For the 5 centimeter active area fuel cell, this is a polarization and impedance plot. We can get the information of the fuel cell performance and the electrode kinetics and resistance information. The anode and cathode loading are 0.048 and 0.056 milligrams per centimeter square, and this measurement conditions are 80 Celsius, 100 relative humidity, and the flow ratio is 1.2 to 2. For the polarization and the impedance measurement, the bank pressure is at 10.5 psig. For the CV plot, it provides information about the electrochemical surface area. The hydrogen to nitrogen flow ratio is 50 to 50 ccm. Before the fuel cell sensor, we need to understand how the proton exchange membrane fuel cell works. So we measure the CV, the polarization, and the impedance at different conditions. The first condition is the dry ambient. We can get the CV curve, and after the humidification, we can get the very obvious hydrogen desorption, absorption peaks, and the oxide formation, oxide reduction peaks. After we increase the bank pressure from 1 to 15 psi, and we continue to humidify the gas, we can get the CV curve at a larger cycle area. We change the electrochemical potential. We can see the similar trend. This is our polarization result. At dry ambient conditions, the performance can reach 1.6 milliampere per centimeter square. And after we humidify the gas and we increase the bank pressure from 1 to 15 psi, we also increase the flow ratio. the performance reaches 0.2 milliampere per centimeter square. At dry ambient conditions, we can see the impedance didn't show a semicircle charge transfer resistance. After humidification, we can see a kind of semicircle curve, and we increase the bank pressure, but we didn't humidify the gas. We can see the impedance is not smooth semicircle. After humidification, we can see the clean charge transfer semicircle. We also observe at a higher current density, the ohmic resistance is decreased for the pink curve. Then we will talk about the PEM fuel cell sensor. This is a configuration. There is a working counter-reference electrode and the membrane as an electrolyte. The nickel is a catalyst here. We will talk about the variable fuel cell sensor for transdermal monitoring of isoflurane anesthetic here. The proton flow from the anode to the cathode, and the generated Faraday current proportional to the concentration of the isoflurane is detected by the amperometric method through the external circuit. The prototype minimized potential stand integrated with a micro fuel cell sensor then can detect ultra-low levels of isoflurane gas. At the anode and the cathode, there is an oxidative addition reaction and oxygen reduction reaction, respectively. During this redox reaction, there is oxidative addition reaction and a reductive elimination reaction. And there is also electrocatalysis. The electrocatalysis focuses on minimizing the electrode over potential, then in turn depends on electrode material, reactants, products, and the intermediates at the interface of the electrode and the electrolytes. The purpose of the electrocatalysis is to enhance the reaction rate, like the produced electrical currents, via the decrease of the activation energy. Here is a fuel cell sensor for detection of the ethanol. The redox reaction at the anode and cathode surface. We can see here the PEM's hydrogen and its ability to transport protons from the anode to the cathode, indicated by the arrow here. The catalyst is to enhance, here is a nickel, enhance the redox reaction rate. At the anode and the cathode side, there is the ethanol oxidation reaction here and the oxygen reduction reaction. The overall reaction is ethanol plus oxygen produces carbon dioxide and water. Here is a fuel cell sensor working mechanism. The electrochemical system obeys the Nernst equation. So the current is determined by the voltage applied, the open circuit voltage, and the reaction speed. This is a prototype watch cell. The fuel cell sensor is integrated here, and the evaporated ethanol is detected from the small window. And the current and the concentration is displayed here. Fuel cell sensor for detection of ethanol. We can apply the multimodal electrochemical technique for improved selectivity based on the OCP and the amperometric. The step one is to identify the OCP in the presence of the humidity. Step two is to apply the obtained OCP value across the working electrode and the reference electrode. Step three is to measure the current flow between the counter electrode and the working electrode. In this process, the current signal due to humidity was eliminated and the current flow due to ethanol oxidation for that particular potential is recorded. Here is a flow chart representing the steps involved in selective ethanol detection based on the OCP value here. From this diagram, we need to point out the impedance at the here negative terminal of the amplifier is very high, which made the current flowing through the reference electrode negligible. Here is a variable fuel cell sensor for the transdermal monitoring of isoflurane. This is a customized printed circuit board and full device prototype. It includes a micro fuel cell sensor here, a minimized potential stand, and the battery. From the two figures, we can see the current output is in linear shape with the concentration of the analyte ethanol and another analyte isoflurane. The watch-style variable electronics, the fuel cell sensor has many advantages, like it has a mini size, low cost, and it is also portable. So it can be applied in the low resource areas. It can potentially replace the IR analyzer in hospital. As we discussed, this is a micro fuel cell biosensor for detection of the isoflurane anesthesia and the detection of the ethanol. For the micro fuel cell biosensor application, there are two challenges. The first one is the selectivity. We try to design the multimodal electrochemical technique to eliminate the interference based on the amperometric method and the OCP. The challenge two is sensitivity. Based on the PCA, principal component analysis, we can improve the sensitivity down to ppm level. As you can see in the linear regression model, when the concentration is very low, the current signal overlaps to a great degree. After the PCA regression, at a low concentration, the current signal doesn't overlap as much as before. So the top two figures are the results from the ethanol, and the bottom two figures are the results from isoflurane. Here, I put the configuration of the micro fuel cell sensor and the watch-style prototype. If we combine the micro fuel cell technology and the artificial intelligence, then we can realize the AI-enabled remote sensing and the decision making based on fuel cell sensor technology.